In this video, we're going to have a quick look at Bayes' theorem and how it relates to probability and, in particular, conditional probability. So the most common question I hear is, what is the difference between this conditional probability formula that we are used to using and we're comfortable with, and now they've introduced Bayes' theorem, which just also seems to be some formula for the probability of something given something. And why do we need to use this equation when this one was working, when this one looks clearly more complicated? And I guess the answer is they do the same thing, these two equations, but they have different components inside them. And when Thomas Bayes, back in the 18th century, when he was exploring conditional probability, he didn't have the luxury of always knowing certain probabilities and events. So this was his first attempt at having a formula for the condition, the probability of something given something, and then this simplified version was developed a little bit after that. Okay, so let's just have a quick look at Bayes' theorem. Now, the two formulas they give you is this one and this one. Now, they are the same formula, but in this first one, this is just assuming that the event B has two outcomes, where if you were to have a tree diagram where we had A, not A, B would just be B and not B. But this second formula here, B, I, and in the formula 1, 2, and 3, this means that there could be actually more than two outcomes. It might be B1, B2, B3. So that's the difference between these two. They are essentially the same formula. Okay, so let's just have a look at the first one. And if we have a look at the denominator, I'm going to simplify this. So I'm going to have the same numerator, the probability of B multiplied by the probability of A given B. Now, the probability of B multiplied by the probability of A given B, this bit here, this is actually just the probability of A and B. And I'll show you why. Because if we just multiply the probability of B up here by the probability of A given B, the probability of B multiplied by the probability of A given B, that is just the probability of A and B. So instead of writing this, I'm going to put the probability of A and B, and then we have plus, and then this is actually the same thing. If I were to write the probability of A given not B as the probability of A and not B over the probability of not B, if we multiply this up, that's what we have here. So the probability of A and not B is this second bit, A and not B. Now what this addition on our denominator actually is if we think about a Venn diagram with events A and B, the probability of A intersection B, that's this intersection, and the probability of A and not B, that's this section here. So this denominator is just the probability of A. So it's going to be the probability of B multiplied by the probability of A given B all over the probability of A. Now this is sometimes what you might see in a textbook as Bayes' theorem. It's the Bayes' theorem simplified version of this here. Okay, so you might think, where are we going with this? I don't see why we need to do all of this manipulation. Now, here's the difference between the conditional probability formula and Bayes' theorem. Bayes' theorem has a formula where it has the probability of B given A and the probability of A given B, both in the equation. And then the only other terms are the probability of B and the probability of A. So Bayes' theorem is essentially just a conditional probability formula, but has both conditions in it. So if you are given one, you can find the other one easily. And you can't do that with this conditional probability formula up here because this has different components. The probability of A given B has the probability of A and B over the probability of B. So this would be useful if you know this and you know this, but maybe we never knew the probability of A and B. And then notice that that's not even in the Bayes' theorem equation of conditional probability. So I guess they are the same, but you will use Bayes' theorem if you know one condition, You might know this one and you want to find this one, or vice versa. And this Bayes theorem links the two conditions together. So if you know B given A, you can use the equation to find A given B. But you can't quickly do that if you just use the conditional probability formula. So how this relates to your IB maths exams, typically you can just use this conditional probability formula up here because you'll be given a tree diagram or a Venn diagram, and you might be given the probability of A and B and B, so you can just use this to find a condition. But you might do a mathematics assignment, or you might get a problem-solving question where they give you one condition and it asks you to find the other condition. And that's where Bayes' theorem is very useful, because notice that in the Bayes' theorem equation, you don't actually need A intersection B. Okay, so if you were happy with the conditional probability formula, you still should be able to get most of these questions correct. But hopefully now you know why Bayes' theorem is slightly different. Okay, good luck.